now we move into chapter X.3 is what we're calling this. It's the continuation of us moving outside of our textbook. What we're going to focus on now is what we call the washer method. This as opposed to what we were using before, which was the disk method. Okay, so this is just another method of finding the volume underneath finding the volume of an area that's revolved around a certain axis and thus creating a solid. So objectives here are to find the volume of a solid if two graphs or more intersect in an area is revolved around an axis. So what we're going to be looking at now is something like what we looked at today in class. If you had let's say two functions, one like this and one like this, okay, that intersected each other. And what we have to realize is we have created kind of this solid, okay, if you kind of shaded all of this in, but then subtracted, so that's the area underneath the straight line. But then what we're going to do is subtract the area underneath this curve. Okay, so here's that area underneath the curve, and what we have left over is just this little smidgen of an area. But then when we revolve that around the x-axis, what we create here is somewhat of a I'm going to kind of draw another image of this same thing. When we revolve that little sliver around the axes, what we kind of create is this hollowed out bowl shape. Okay, so you can kind of see it looks like a solid from the outside. That's what it would appear. But then if you actually kind of pivoted this to look towards us and we slice this, what we would be getting are not discs anymore, not solid discs, but what we would get are washers. It would be a disc minus kind of another inner disc from in between it or from within it. So if you could kind of picture slicing this hollowed out bowl, what you're going to get are these washers. Okay, so the other thing that you need to do is solve for intersection points. What you're going to find is sometimes it's going to be to your benefit to find these intersection points because those are going to be the A and the B, the lower and upper bound that you need to focus on. Okay, so there are our objectives. We're going to look at this problem right here. And what we're going to do is find the volume of the solid formed by revolving the region bounded by y equals 4. I've graphed that in blue. X equals 0. I graphed that in pink. And y equals 1/2 x plus 2. Here is just slope-intercept form. There's my intercept, so there's my 2. And then rise over run, so we rose 1, went 2, rose 1, 1 over 2, or ran 2. So there is that green line that's associated with that linear graph. And what you can see in here is that I've colored in this I've shaded in this region, and that would be just the area. You could easily find the area of that. But now what's happening is we're revolving this around the x-axis, so what we're going to be doing with this area is creating a solid. So I found this excellent website. It's called mathdemos.org. And what it basically does is it just shows a bunch of, this right now they're revolving around the y-axis, but if you had a function from, let's say, 0 to 4, and you revolved it around the y-axis, this is what you're showing. And some of these disks are solid, some of them aren't. Okay. Some of them have those little holes in them, which are therefore washers. So I mean, any one of those discs you could, or any one of these rectangles you can take and rotate around, and what you are going to be creating are either discs in this method or these washers. Okay. So wholly, if you went all the way around, what you would be forming is what appears, as I said, a solid on the outside, but actually we have those hollowed out regions on the inside. Alright, so here is kind of like what we looked in class today, except it's tilted it towards us, and so you can see what this is looking like. And someone had mentioned today in class that would it look like a bowl, and yes, you can kind of see how that looks like a bowl. And keep in mind that imagine yourself slicing these. You're getting these washers that are some very thin washers, some very thick washers. Here today, someone in class also said, what are washers? There they are. Finally, we have this. This is the kind of graph that we're looking at, the one that I just graphed out on the side and that we'll go back to. So once again, what we can see are the widths of these rectangles are what we're calling delta x. And then the heights of these rectangles are going to be the difference of our upper curve minus the lower curve. And what we are going to get then is eventually we're going to revolve these rectangles around, and what we're going to be looking at are disks minus an inner disk. So we're going to be finding what is this larger disk's volume, and then we would also subtract off of it this lower disk that's created when you take that those bars underneath this lower graph and revolve it around the axes. Here's the equation, and what I wanted to kind of point out here is right here is this is the volume of the big disk, and we're calling g of x, that's the radius, that's the larger radius of the two. That one is the one that's the curve on the top. Okay. All right, and then this right here is going to be the volume of your small disk. You're only going to be going up to the radius of the smaller curve. So what you do see here is we do have this pi r squared times width of both of these cylinders. So you can pull out that pi. You can also pull out that width that they have in common, or the delta x that they have in common, and if you were to distribute that back in, there is a minus sign there, sorry. If you were to distribute both of those back in, you would get this exact equation. So this is the most simplified version that I'm going to be working with. This is what I'm about to use as I actually solve for our problem that we started out with. So moving back to here, I will write that down. So it helps when you don't have to memorize these. This is, if you can kind of use that reasoning or that technique of knowing that you're to a point using the disk method and you're using pi r squared, but now you're going to factor out that pi and the dx, and then all you have to do is be taking your g of x squared minus your f of x squared. I'm going to use this formula and I'm going to now fill in everything that I know. This is my upper function. It is the line that creates the larger washers. So I'm going to be looking up to this line. This is my g of x. So if you want to, sorry, I kind of scribbled over this before. We have g of x is equal to 4 because that I visually can see is my upper. So it's going to be the big disk. So here I am going to have to solve for my a. You can kind of see that a, where does this bounds end, or this binding point end? It's the 0. If you need to solve for this point, because you can't always trust your graph, you know it's the intersection of two lines. You know it's the intersect of y equals 4 and then y equals 1/2 x plus 2. So what I'm just going to do is set them equal to each other and solve. And when you do that, subtract 2, we get 2 equals 1/2 x. I'm going to just multiply by the multiplicative reciprocal to get rid of that, which means I multiply here. 4 equals x. And you can kind of see that because I did a fairly decent job at graphing. So sometimes though you can't really tell, so you are going to have to solve it like this. G of x, like I said, is that 4, so I'm going to take 4 squared minus f of x squared, so that's going to be that lower bounds of this region or of that area, and we're going to just plug that in, 1/2 x plus 2 squared, and then we got our dx. Okay, so there's a couple ways that we can go about finishing this off. I'm going to go ahead and put that pi on the outside once again, and we're going to integrate from 0 to 4, and I'm going to write just this as 16 minus, and then I am going to keep this 1/2 x plus 2 squared dx. If you wanted to FOIL this out, you would eliminate the fact that you have a composition here. So you could take 1/2 x plus 2 times 1/2 x plus 2, FOIL that all out, and you'll just get individual terms. But I am going to just use the chain rule here, so I still have that pi, and then the integral of 0 to 4, 16 dx, and then I have minus, I'm going to keep this in parentheses, the integral from 0 to 4, 1/2 x plus 2 squared dx. And now what I would just have to do is integrate each one of these separately. So I'm going to do that. We have pi, and then in parentheses, I'm going to integrate this piece because this is not too bad. I just have a constant integrating it with respect to x. So when you integrate a constant with respect to x, you're just going to get 16x. And I am going to write the fundamental theorem notation. We're eventually going to plug 4 and 0 into here. And then minus, okay, this I'm not going to quite integrate yet. Okay, so I'm going to rewrite this as a u, as a composition function. U equals 1/2 x plus 2, and then du, the derivative of u with respect to x, so I'm going to derive this with respect to its variable, you get 1/2. Okay, when I multiply dx to both sides, this is what I get. And then notice, remember, we're trying to get dx out. There is no 1/2 attached to it, so I am going to multiply this by 2. I'm going to get 2 du, so that's gone. So now I'm going to replace this dx with 2 du, so 2 du. And then I'm going to replace my 1/2 x plus 2 with my u squared from 0 to 4. So now I am going to pull out this 2, bring that to the front. So we have pi, and then we still have the 16, x. But then you have minus. Now I am going to integrate this, so I'm going to drop my integration symbol, and I'm going to get u to the third divided by 3, but I am going to plug my u back in. So I have 1/2 x plus 2, that's my u, to the third divided by 3, which I'm going to write as 1/3. And then, I almost forgot that 2. So that 2 is out here, so I'm going to multiply that 2 back on. And then here I have from 0 to 4 as well. Okay, so now fundamental theorem all the way. Alright, so I'm going to plug in, this is a 16x, sorry I had to scribble that in. So we had a 16 times 4 minus 16 times 0. That's that first little piece. Okay, and all of this, don't forget your pi is still out here. Minus, and you're going to plug in your 4. So you're going to get 2/3, this is all together as well, 2/3, 1/2 times 4, so I'm just going to write 2 plus 2, which is 4 to the third, minus 2/3, and then when you plug in your 0, you're going to get 0 plus 2, so 2 to the third. Okay, so there's the fundamental theorem at work right there. So we have pi, and this simplified would be 16 times 4. So we have 64 minus 0, so that's the first term. Minus, when you simplify all of that, this you don't get a very pretty number. You're going to get 128 over 3. And then minus, this right here is 8 times 2, 16. 16 divided by 3. So this simplified by 64 minus, and then we have 112 over 3. And if you can just go ahead and calculate this in your calculator, what you are going to get is approximately 83.73 units cubed because it's volume. So there we have it. That's it.